Here's another kinematics question, which we're gonna approach without actually using Euler's equations this time around. Okay, so let's see what we have. So we've got this rod OA, right? And then you've also got a hydraulic cylinder that's labeled as C, right? And then at the end of this piston connected to the hydraulic cylinder, there's a collar, right, which is denoted as B. And B has a vertical velocity that's given to us as just V, right? So we don't have any numbers in the question. And what we know is this distance. We know this distance at this particular moment in time. And we also know this velocity, right? Now, the question is, what is the angular velocity of the rod as a function of, so that's what this notation means, right? What's the angular velocity of rod OA based on, or as a function of the velocity, the vertical distance S, and the horizontal distance D, okay? And let's try to do this without Euler's equations this time. And let's try to think things through a bit. So we know that collar B has purely a vertical velocity, okay? So this is what we have. We have collar B, which is inclined at an angle of theta, right? And it's moving upwards with a velocity V, like this. Let's make it into a vector as well. And then, based on that, how can we actually find anything useful? Well, if you think about it, that rod OA actually goes through the collar, right? Which means that, let's try this. This collar has two velocity components. One velocity component is parallel to it, right? And the other one is perpendicular to it. So this one I'm going to call Vn from the normal component, and this one I'm going to call Vt from the tangential component. So the thing about this velocity, if you think about what happens to the bar that goes through the collar, the bar at point B, so within that collar you have the bar going through it, and where point B actually is, the normal velocity of the bar at this point has to be equal to Vm, right? So this Vb, let's call it. So this velocity has to be equal to Vm. Now, why does this have to be equal to Vm? Well, that's because those are two solid objects, right? And you cannot have two solid objects in contact with each other having different velocities perpendicular to each other, right? Because, for example, if this velocity was greater than this velocity, or the other way around, it means the collar would go through the bar, which it's not possible because those are two solid objects, right? So we must have the fact that VB is equal to Vn. And this is the key to solving this question. And from this point on, it's just doing a bit of trigonometry until we get the final result. So we have an angle theta, but keep in mind we don't actually know what theta is. It's given to us on the diagram, but the question asks us to find the angular velocity based on only those three things. Okay? So we're going to deal with theta separately, but before that, let's let's try to find Vn. So this angle here is also theta if you do a bit of geometry, which means that Vn is actually V cosine of theta. Okay? Which means that the velocity of the bar at point B is also V cosine theta, because as we just discussed, Vb is equal to Vn. Now, the only thing we still don't know is what cosine of theta is, because, yeah, theta is given to us, but we have to use the other things. So what we're going to do here is we're going to say that cosine of theta equals, and this is a right-handed triangle, right? This here is a right triangle, which means that theta is the adjacent side divided by the hypotenuse. So the adjacent is d, and the hypotenuse we can find out with Pythagoras, which is the square root of d squared plus s squared. Okay, so this is cosine of theta in terms of other things that are considered to be known. So VB is equal to V times cosine of theta, which is d over square root of d squared plus s squared. Okay. And let me draw this bar here again, because it's going to be hopefully obvious that, so the bar is hinged here, point B somewhere here, and the velocity of point B, as we discussed earlier, it's actually perpendicular to the bar. And it has to be perpendicular to the bar, right? Because the bar is fixed here at point O. And if it wasn't the case, if VB was slightly tilted to either side, then it means that bar would fly off from the hinge, which is not the case. So we can therefore say that VB is also equal to omega, and that's omega OA, right? That's the angular velocity of the entire bar, multiplied by this distance, which is, of course, our hypotenuse, right? That's the square root of d squared plus s squared. So to find omega from here, we just rearrange. So omega OA is VB divided by square root of d squared plus s squared, which is V times d over d squared plus s squared, because those two square roots get multiplied with each other, so they cancel out, and that's it. That's the final result. All right, so in this case you can see that omega turns out to be positive, which makes sense because the bar is rotating counterclockwise, and yeah, that's it. That's the end of the question. So this is a kinematics problem without using Euler's equations.